Hello, everyone. I'm Mihir, and this summer I worked under Dr. McNamara at the University of Louisville, and my project is on non-volatile computer memory using bistable mechanical beams. Modern computing stores memory on a hierarchy. On the top, you have your CPU and cache. In the middle, you have DRAM, which is fast, but it's volatile, meaning when you cut power, all data in it is lost. And on the bottom, you have flash-based SSDs, which is non-volatile, but they're super slow. The issue is data is constantly moving between these layers on the hierarchy, which slows stuff down, and it's a really power-intensive process. So our approach is to combine RAM and SSD together to create one unified memory to reduce the copyback delays. So data will be stored in one place, making systems simpler, faster, and cheaper. And we're gonna store this memory in a mechanical way rather than the traditional charge-based methods. So how is this MEMS beam gonna be made? The MEMS beam is gonna be a titanium tungsten alloy, and the substrate is a silicon wafer, and it's gonna be separated by an SiO2 layer. So first, the tungsten is etched away to create the shape of the beam, and then the silicon dioxide is etched away to create an air gap between the tungsten and the silicon wafer, allowing the beam to bend up and down, representing zeros and ones, binary digits, and it holds position without power, making this non-volatile. So how does this work? On the top, you can see that is how the setup is going to look like. There's going to be two electrodes, one on top of the electrode, one below the electrode. And if we're writing a bit value, let's say you want to write a 0, you apply a voltage pulse to the bottom electrode and the beam bends downwards. If you want to write the bit value as 1, you write a voltage pulse onto the top electrode and it bends upwards. And to read the bit value, since the electrodes have capacitance in them, whichever side the beam is closer to is going to have a higher capacitance. So since I is C dV dt, in the picture on the bottom, I2 is going to be greater than I1, and that's going to go into the sense amplifier, which is what I worked on this summer, the reading component of the project. So my first design started off with me researching a lot of different dynamic comparators, and this is the first design I came up with. I spent the majority of my time on this design. This was a two-stage comparator. Stage 1 pretty much took the current inputs and kind of worked through it, making it into a much more dealable voltage, and then stage 2 amplified it further. Those are the results for the first comparator. As you can see, the higher the voltages were amplified. The higher voltage goes up to 5 volts, and the lower voltage goes up to 4.3 volts, which is all right because we can find a difference in voltage between both the outputs. But the issue with that was we cannot integrate it into a full CMOS layout. So then I tried to look about it a little more, and then I found the strong arm latch. So the strong arm latch, this is how it looks like. It has an input differential pair, M1 and M2. They sense the input currents, and a higher input conducts more current. M3 and M4 are an NMOS cross-coupled pair. M5 and M6 are a PMOS cross-coupled pair. M7 is the tail current. It is a clock-controlled switch. M8 is used for output load isolation, and M9 and M10 acted as pre-charge transistors for resetting the entire circuit after each cycle. So looking at each individual phase of the circuit's operation, phase 1 is when the clock is low, the tail current is off, so there's no current going through the inputs. It recharges all the nodes on the circuit to VDD. For us, it was 5 volts. This is to remove previous memory effects. Phase 2 was the amplification stage. That's when M7 is turned on, the clock is turned on, the input M1 and M2 gets current in them, and the higher current translates to higher voltage inside of them. And then phase 3 is when the cross-coupled pairs, M3 and M4, M5 and M6 start working. They create exponential positive feedback. The circuit pretty much reinforces itself, saying this output is higher and this output is lower, taking one output to 5 volts and one to 0 volts. The advantages of the circuit is that this is a zero static power circuit, it's a high-speed circuit, and it also gives rail-to-rail outputs. These are the simulations which I ran. As you can see on top, the inputs are a super small number, where the higher input current is going to be at around 1.2 microamperes, and the lower input current is at 0.459 microamperes. And the output suggests that we did get a proper output. The line is flat over here, the green line and red line are overlapped. That's when the clock is off. The entire circuit is pre-charging itself. And then when you see the sharp drop in the green line and the red line rises up to 5 volts, that's when the circuit is actually working. The voltage gap allows us for clear memory detection, but the issue with this circuit right now, at least, is that it's not going completely down to 0 volts, which should be worked on ahead. After that, I designed a photomask. I designed it using a 250 nanometer process, and the photomask includes layers for different metals, for wiring, active regions for transistor regions, poly for gates, contact for connections, and also vias for connection between multiple metals. I had to follow strict design rules for spacing, minimum width, and alignment. At the end of this project, I simulated and designed a clock current comparator for the MEMS beam memory cell. It reliably detected the small input currents, enabling fast and accurate movements. I completed a 250 nanometer CMOS process. The next steps for this project would be to get the lower output I mentioned before down to 0 volts, and to further modify this layout, because as you can see over here, there's some excess space. It's always nice to get everything closer together, and to manufacture this photomask for fabrication, connect it to the actual MEMS beam so that we can check if it actually works. I'd like to thank my mentor, Dr. McNamara, for giving me this amazing opportunity, the NSF, and Ana Galeano Sanchez for giving me, for conducting and hosting the entire program really smoothly. Yeah. Any questions?
Great presentation.
Thank you.
Any questions, anyone? No questions. Okay, well, thank you.
Thank you.